We have talked about the normal and the multi-normal distributions. Now, we shall talk about a related distribution which is denoted by this symbol and is called the chi-square distribution. It is defined via normal distribution like this. We start with x1 to xn iid normal 0, 1. So they are jointly distributed random variables. Hence I can compute summation xi square I going from 1 to n. That's another random variable. Now any random variable has a distribution. So this also has a distribution. It is this distribution that we define to be chi-squared. Now you naturally expect that this n should appear somewhere as a parameter, and indeed it does. I shall write it here as a subscript. This little n has a special name. It is called the degrees of freedom. So this random variable has distribution chi-squared with degrees of freedom equal to little n. Now this definition is somewhat roundabout in the sense I have not given you it's a PMF or PDF or whether these things exist or not. I have given you basically like a random experiment, how you can generate one such chi-square random variable. And this definition is what is useful most of the time. You really do not care about its PDF, etc. But in case you are interested to find its PDF, that turns out to be pretty easy once you learn an interesting theorem. The theorem links up the chi-square distribution with a distribution that we already know, the gamma distribution. Chi-square n is gamma half n by 2. Now the order of these two parameters, there is no unanimity among various sources. So I will quickly remind you the definition that I am using. When I write gamma p alpha, I mean this density. So p is the parameter that occurs in the exponential and alpha is the parameter that occurs inside the gamma. You can remember them as the rate parameter and the shape parameter. The first one is the rate parameter, the second one is the shape parameter. Now in this proof, we shall first work with the n equal to 1 case. So according to our definition, here we have to think about only one normal 0, 1 random variable x1, and the sum now reduces to just x1 square. So the distribution of x1 square is chi-squared with degrees of freedom 1. So let us find out its distribution function. From that we shall work out its density and check against this to see whether I really get the parameters right. So this is the distribution function. Now this is same as probability that x1 lies between minus root a to plus root a. Of course we are working with a positive because if a is negative then this anyway is equal to 0. Now I know that x1 has normal distribution, standard normal, so we know its density, hence this one equals this integral. This is the normal density and I am integrating from minus root a to plus root a. Pictorially it is this area. Now I know it is symmetric around 0, so it is enough to work out only half of this and just double it. So this actually equals, make it from 0 and double it, put a 2 over here. My next plan is to differentiate it with respect to a. This a occurs upstairs. The problem is it occurs at root a. So it will help if I write it as g of root a, where g is the integral from 0 to t of the normal density times 2. Now I can differentiate f by using chain rule. I first differentiate g dash to root a, and then I differentiate root a to root a. Now g dashed can be quickly computed from here merely by bringing the t down. So g dash t is, forget about the integral, tx, and in place of x you just put t. So this will become a to the power minus half, then g dashed a, that will become e to the power minus a by 2. I had t square here and I put root a there in place of t, so I get minus a by 2. And I do not care about the constant because I know it's a density, so the constant will take care of itself. Compare this with this and you will immediately see that if I consider this minus half as half minus 1, then you have to take alpha equal to half and p equal to half. In that case, the constant again must naturally match because this is a density, that's a density, so the constants must match. In fact, this will give you an indirect proof that gamma of half can be expressed in terms of pi. Okay, so we get that this is indeed the density of gamma half half, and that's what we wanted to show for n equal to 1. Next, let's get to the case of general n. So using our definition of chi-square with n degrees of freedom, we shall start with x1 to xn, id, normal 0, 1, and then this will be the distribution of x1 square plus dot 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 up to xn square. Now from this case, we already see that each one of them has a chi-square 1 distribution, so each of them are actually gamma half half. And also they are all independent because all the xi's are independent, so xi squares are also independent. Now we know from a result about gamma that if I have independent gammas and I am adding them up, and these independent gammas all have the same rate parameter, then their shape parameters will add up. If u and v are two random variables that are independent, u has distribution gamma p alpha 1, v gamma p alpha 2, same p in both the cases, then u plus v will have distribution gamma, same p, but alpha 1 and alpha 2 will add up. Now I shall use this again and again because in all this case I have the first thing half, so this will have distribution which will be gamma again, the same parameter half, but all these halves, n many of them will add up to give me n by 2. And that's precisely this. We know that the distribution of this is defined to be chi-square n, so we have shown chi-square n is same as gamma half n by 2. So we know how to write down the density of that. Immediately we know how to write down density of chi-square, mean, variance, etc. all can be obtained from properties of the gamma distribution. In this exercise, you are required to find the characteristic function of the chi-square with n degrees of freedom. I give you a hint that characteristic function of gamma p alpha is given by p divided by p minus it whole to the power alpha t in R. So we already know how to write chi-square in terms of gamma, so just obtain the characteristic function of chi-square n.